Permutation of n objects taken r at a time. A permutation of n distinct objects is an ordering of objects or arrangement of objects. If the arrangement of writing will change, then the permutation will change. For example, if we have a set consisting of 3 elements, let set A consists of 3 elements 1, 2 and 3. We are going to write all permutations. Write all permutations. All permutations. Permutations. And of course we will be using all elements. Using all 3 elements of set A. The first permutation P1, that would be 1, 2, 3. So that would be first permutation. Let's keep it in the form of set, and P2, it would be equal to, will have the first element same, will switch over the second and third element 3 and 2. Certainly this is a different arrangement of writing numbers, so essentially this is called a different permutation. P3 would be equal to 2 and 1 and 3, and P4 is equal to 2 and 3, 1. So this is a different arrangement. This is a different permutation. P5, the first element we are going to keep 3 and we'll switch the second and third position. So this will be 1 and 2. And P6, the sixth permutation, is equal to 3, 2 and 1. This is what we mean by permutation of n objects. There were 3 objects, and using all of those objects we wrote down all the 6 permutations. If we take an alternative approach, taking a different approach, what happens if we have 3 objects? How many ways we can fill in the first position? So first position, second position and third position. To fill out the first position, 1 or 2 or 3, there are 3 different choices to fill up the first position. So there are 3 different choices to fill up the first position. Once the first position is filled, then you can see in the above permutations, the first position could be 1, which we did here and here, or the first position could be 2, which we did in P3 and P4, or the first position could be 3, which we did in P5 and P6. So there are 3 choices to fill up the first position. So once first position is filled, how many choices do we have to fill up the second position? Because one element is already used, which is not going to be repeated. That's why we have only 2 choices, 2 elements left behind to fill up the second position. And once the first position is filled up, the second position is filled up, then how many elements we have available to fill the third position? If we want to keep all elements distinct, then the third position will have only 1 leftover element, which will essentially fill the third position. So the total permutations will be permutations will be equal to 3 times 2 times 1, which is equal to 6. So this is exactly in accordance with the first principle of counting. If we take a different approach and we repeat elements, like 3 3 3 is also a possibility. So repeat elements. If that is the case, then how many elements are available to fill up the first position, second position, and third position? This time, if the elements are repeated, then the first position can be filled up with any of the three numbers, 1, 2, or 3. So obviously there are three different choices we can fill up. Now because numbers can repeat themselves, therefore for the second position again there are three choices, because we can repeat a number. Doesn't matter if it was written on first position, we can write it in the second position again. So three choices are available for second position, and similarly there are three choices to fill up the third position again. So according to first principle this time, so according to first principle of counting, the total permutations would be 3 power 3, which will be equal to 27. This is if elements are allowed to repeat. But if elements were not allowed to repeat, then there are 6 permutations. Now we will do few questions in order to elaborate more on this concept. Here we have n objects. So in this example here, total objects are n, and all these n objects are obviously distinct objects. And if we take only r of them at a time, then calculate the number of permutations. If r of these objects are used at a time, then find number of permutations. In other words, we can write the same question as n means the total number of available objects, distinct objects, p for permutation, r of them are being chosen, and we are going to prove that this is equal to n factorial over n minus r factorial. This is what we want to prove, that out of total n distinct objects, if r of them are being used at a time, then the total number of permutation is equal to n factorial over n minus r factorial. Let's get started with this. The first position, so elements available to fill first position is equal to n, because all n distinct objects, any one of them could be used to fill up the first position. But once this first position is filled up, then how many objects are available to fill second position? So for second position, the number of elements, second position is equal to n minus 1 because one of them is already used. That's why we have one less than the total number of distinct objects. If we want to fill up the third position, so for third position we have how many elements? One less than n minus 1 because in the second position another element has been used, so this time there will be n minus 2 elements. And similarly, if we want to fill up the fourth position, how many elements are available? This time there are n minus 3 elements. There is an interesting pattern you can see that for fourth position there are what is number being subtracted from n, that is 1 less than 4. If it is 4 here on left side, there is 3 on the right side. And if it was 3 on the left side, then the number being subtracted is 2, that is 1 less than 3. And similarly, if it was second position, then what is being subtracted from n, that is 1. So clearly, if we continue with this pattern and we want to fill up the rth position, then what should be subtracted from n? We should subtract a number 1 less than r, which should be r minus 1. If this is what is being subtracted, then according to the first principle of counting, then according to first principle of counting, the total permutation, NPR, number of permutations for n distinct objects taken r at a time, is equal to n, product of all these elements which are available for first, second, third, fourth and rth position, is equal to n time n minus 1 time n minus 2 time n minus 3 and so on up to n minus r minus 1. Here we use double bracket, but n minus r minus 1, if you open this up, this would become n time n minus 1 time n minus 2 time n minus 3 time n minus r plus 1. And if we multiply and divide with a factorial of element 1 less than this, that would be n minus r factorial. And because we are multiplying n minus r factorial, we also can divide this whole thing with n minus r factorial. It doesn't make any difference if we divide and multiply with the same number. But what is the advantage of this multiplication? That in the numerator we have a product of consecutive natural numbers all the way up to n, and therefore this can be written as n factorial, and this is divided by n minus r factorial. So that is what was required. Sorry, this was NPR. P stands for permutation. So here now we can say that NPR, this is an established formula, NPR is equal to n factorial divided by n minus r factorial. and we'll use this formula to solve now questions. And the next question we have is, how many distinct 4-digit numbers can be formed out of the digits 1, 2, 3, 4, 5 and 6. So there are 6 digits and we want to find out the numbers which can be made by using only 4 digits. So n in this case is equal to 6, and how many are being used at a time? R is equal to 4. This means that NPR, this would be, R in this case obviously is 4, but that's what we are going to write in next step. 6P4, this is equal to 6 factorial divided by 6 minus 4 factorial, and this is equal to 6 factorial divided by 2 factorial. This means this is 6, 5, 4, 3, 2, 1 and divide by 2 times 1. So this 2 times 1 is cancelled with this 2 times 1, and now what we are left with is this 6 times 5 is 30 times 4 times 3 is 12, and this is 360. And if the repetition was allowed, if repetition was allowed, then first position, second position, third position and fourth position, here all 6 would be available, all 6 would be available, all 6 would be available, and all 6 would be available for all the 4 positions. Therefore number of elements would be 6 power 4, which of course can be simplified. And if we take a look on the next question is that how many signals can be made with 4 different flags when any number of them are to be used at a time. So if we are to use only one flag to signal, so this is example number 3. One flag. If we use one flag, then N is equal to 4 and R is equal to 1. This means that 4P1 is equal to 4 factorial divided by 4 minus 1 factorial, which is equal to 4 factorial over 3 factorial, which means this is equal to 4. If we use two flags, then N obviously is equal to 4, but R in this case is equal to 2. Therefore 4P2 is equal to 4 factorial divided by 4 minus 2 factorial. So this is equal to 4 factorial over 2 factorial. If we want to simplify this, this would be equal to 12. And similarly, this time we are going to use 3 flags. If we use 3 flags, then N same way. This is 4P3 and this would be equal to 4 factorial over 4 minus 3 factorial. So the number of permutations in this case would be 4 factorial over 1 factorial, which is equal to 24. And if we use all four flags, using all four flags, 4p4, this is equal to 4 factorial over 4 minus 4, that is 0 factorial. So 4 factorial over 0 factorial, and if you remember, we know that 0 factorial is equal to 1. Therefore, this is equal to 24 again, and the total number of permutations, total number of permutations is equal to 4 plus 12 plus 24 plus 24, and this will become equal to 64. So this is 64. Now the last example for this lesson is that we have a space of 9 books. In how many ways can a set of 4 different mathematics books and 5 different physics books can be placed on shelf with a space for 9 books if all books on the same subject are kept together? So how many variations are possible for 4 different math books? So we can write example number 4. Example 4. So permutations for math books. Those are equal to 4p4, because we will be using all 4 of them, and this will be equal to 4 factorial over 4 minus 4 factorial. This means this is equal to 4 factorial over 0 factorial, but 0 factorial is equal to 1. Therefore, this is equal to 4 factorial. And number of permutations for physics books, number of permutations for physics, those are total 5 books, so these are 5 factorial. Same way, we had 4 factorial for 4 math books. We have the permutations for physics, same 5 factorial. And now if physics books are treated as one block and math books are treated as another block, then the permutations for two blocks of books would be equal to 2 factorial. And if we apply the fundamental counting principle by applying fundamental counting principle, what we have, total number of permutations, total number of ways, or you can say permutations, is equal to 4 factorial time 5 factorial time 2 factorial. So this gives us the total number of permutations.